Okay, so if you didn't look at this example problem, go back and look at it. Okay, I'm just going to go on kind of a rant and explain how it is that if we pull a mass in like this, okay, not only does the angular velocity have to increase because the moment of inertia decreases, but the actual linear velocity of this thing increases. In fact, in this example, it starts off at 2 meters per second, okay, and it ends up going 42 meters per second. And then the more you pull it in, the more pronounced this is. Now, in a real life experiment, you would find that you wouldn't get exactly that because it's hard to go 90 miles per hour through the air. You'd have a lot of frictional losses. You need to do this in a vacuum or some sort of frictionless thing. But you really will increase the velocity. It's not just that it appears to go faster, okay? It actually goes faster. The linear velocity of this thing actually increases, okay? Now, why? First, let me explain that it has to go faster, okay? If I exert a force and I reduce this radius, I've exerted a force over a distance, right? Okay, and we know that work is force times distance, right? So we know that we've done work on this mass, right? And if you do work on a system, there's something called the work energy theorem that states that if you do work on something, you have to increase its energy, okay? The energy of that system must increase. Well, all this thing has is kinetic energy. That's all it's got. As this thing spins around, it's just got really, it's 1/2 mv squared. In fact, it's rotational kinetic energy, right? 1/2 I omega squared, right, is equal to 1/2 mv squared. That's all it is. That's all it's got is that 1/2. Let me just show you this, right? I would, in this case, be mr squared. Omega is just v over r, and we square that, right? And you can see, without really spending a lot of time, that it's exactly the same. 1/2 I omega squared and 1/2 mv squared are exactly the same thing, right? Okay, so that means that if I do work on that system, this thing, which only has kinetic energy, has to increase its energy. Therefore, it's got to increase its kinetic energy. Therefore, it's got to increase its velocity. Okay? Now, the question is, how? How does a force that is radially inward actually speed something up that's moving at right angles to that force? And the answer to that is that the force is not at right angles to the velocity. And let me explain why. Okay? I'm going to erase this stuff, okay? If we're not pulling it in, yes, it's true that this velocity is perfectly at right angles to this, right? And so the force that we're exerting toward the middle, right, whatever that force is, that force doesn't do any work on this object, and that's because the angle between the velocity and the force is 90 degrees. But if I'm pulling this in, then it's not moving perfectly to the side, is it? Right? It actually has a downward component of velocity, right? It's moving in. I'm pulling it in, right? So its actual velocity is like that, okay? So now as I exert a force on it, some of that force is actually in the direction that this thing's moving. And so as this thing spirals in, it goes faster and faster because I'm actually exerting a force that's a little bit in the direction that it's moving because it's moving a little bit inward. Okay, so Newton's laws would say that if we exert a force that's a little bit in the direction that an object's moving, the object's going to speed up, and that's what happens here, right? I literally speed this thing up because it's going to spiral in, right? It's going to like that, right? And as I pull it in, my force is a little bit in the direction of the velocity. So that's how it actually speeds up, which just kind of seems magical, but it's not. It's just Newton's laws.